100 candidates. One job. They arrive in random order, one at a time, and after each interview you must decide on the spot. Hire or reject forever. No comparing later. No calling anyone back. Hire too early, and the best is still out there. Hold out too long, and you already sent them home. It feels like a problem with no right answer, a pure gamble dressed up as a decision. It is not. There is an exact strategy and an exact number, 37. Reject the first 37, whatever happens. Then hire the first person better than all of them. By the end of this video, that number will feel less like a trick and more like a law. First, the rules of the game, stated honestly. You know how many candidates there are, say N. They arrive in uniformly random order. You can always rank the ones you have seen, who is best so far, who is second, but you learn nothing about the ones still waiting. Each decision is final. And the goal is maximalist, not someone good, but the single best of all N. Anything less counts as failure. Strict rules, but they buy us something rare. A messy human dilemma becomes a machine we can take apart. Take it apart at the smallest size, 3 candidates. 6 possible arrival orders, we can list them all. Strategy 1, hire the first person. You win only when the best arrives first, 2 orders out of 6. Strategy 2, always wait for the last, same 1 in 3. Now the clever middle path. Let the first one go, then take anyone better than them. Count it through all 6 orderings, it wins in 3. 50% from pure position play. No strategy does better at N equals 3. The skip is not hesitation. It is calibration. The first candidate becomes your measuring stick. Now the general machine. Skip the first R-1, then take the first record, the first candidate better than everyone before. The success probability has a closed form. R-1 over N times the sum of 1 over K-1 from R up to N. Read it as a bargain between 2 failures. Skip too few and your measuring stick is weak. You settle early for a false best. Skip too many, and the true best was probably in the pile you burned. Somewhere between the two sits a peak. For 100 candidates, the formula says, the peak is exactly at skipping 37. Don't trust the formula, run the hiring season. 200,000 random orderings of 100 candidates, every cutoff tested. Skip 10, you succeed 23% of the time. Skip 60, down to 31. Sweep the whole curve and watch the crest form, right at 37. Success rate 37%. Both numbers are the same because both are wearing the same disguise. 1 over E, the base of natural growth, 0.368. Euler's constant, hiding in a hiring committee. YE. Let the cutoff be a fraction x of the field. For large N, the success probability approaches a clean function, x times the natural log of 1 over x. Success needs 2 things at once. The best must come after your cutoff, and the runner-up of the early field must fall before it, guarding the gate. Multiply those tensions and you get the curve. Calculus finds its maximum where the derivative vanishes. X equals 1 over e. And the height of the peak is also 1 over e. The cutoff and the success rate agree, not by coincidence, but because both are the same number, the balance point between learning and committing. The problem has a marriage in its past. 1611, the astronomer Johannes Kepler, newly widowed, begins a famously methodical search for a second wife. 11 candidates, 2 years of interviews, agonizing letters comparing them all. He passes on candidate 4, then chases candidate 5 after seeing the rest. She says yes. 3.5 centuries later, Martin Gardner prints the puzzle in Scientific American, 1960, as the game of Google, and the mathematics of when to stop looking becomes one of the most resolved problems of the 20th century. There is a deeper law underneath, found by Franz Bruss. Any stream of chances, candidates, offers, windows, where each moment might be a record. Compute each moment's odds of being one, then add those odds from the end backwards. Stop being picky exactly when the sum reaches 1. For our 100 candidates, position K is a new best with probability 1 over K. Sum the odds from the back and they cross 1 precisely at position 38. The 37% rule falls out as one case of a single sentence. Act when the remaining luck adds up to 1. One honest objection, only the best counts. Really? In life, the second best of 100 is wonderful. So change the goal. Minimize the expected rank of whoever you hire. The strategy changes shape instead of one cutoff, a schedule of slowly relaxing standards. Early on, accept only the best so far. Later, second best is fine. Near the end, take what comes. Dynamic programming gives the exact answer. With 100 candidates playing optimally, your hire's expected rank is about 3.6. Out of 100. The lesson survives softening. Calibrate first, then commit, just less brutally. The rule bends gracefully under real-world friction. Suppose each offer is refused half the time. The math says start committing earlier, around a quarter of the field. Suppose you can return to one old candidate and they might still say yes. Wait longer. Suppose you don't even know how many candidates will show up. Then switch from counting people to counting time. Commit after 37% of your search window has passed. Every twist moves the threshold, but the architecture never changes. An observation phase, a commitment phase, and a switch point you can compute. So should you actually live by 37%? Apartment hunting in a hot market is the textbook case. Listings vanish in hours, there is no going back, and the field is finite. Give the search a month. Spend 11 days looking without leaping, calibrating, then sign for the first place better than everything you saw. Parking near a venue, hiring on a deadline, selling into a stream of offers. Same shape. But remember what the model assumes. No revisiting, only the best counts, random order. Real life is softer on all three, so treat 37% not as a command, but as a calibrated permission slip. After a third of your search, stop browsing. Choosing well was never about seeing everything. One dilemma, one number, three faces. 37% of the field, your training data. 37% success, the best you can do. 1 over E, the reason they match. The secretary problem takes the anxiety of choosing under uncertainty and shows that even here, no information, no second chances, mathematics finds the exact border between looking and leaping. Look with the first third. Leap with the rest.